1.3 Organizing Data. Presenting scientific data, we use graphs and tables. Types of graphs include circles. Those show parts of a whole. So when we're doing percentages, that's when you would do a circle graph, or you might have learned it as a pie chart. A bar graph is used to compare things, so different things. A line graph shows change over time. If it's a single line, it only has one dependent variable. If it's a multi-line graph, like the one you see here, there are two or more variables that are being measured. A scatter plot is used to observe relationships between variables. You can see how there's just dots all over the place. In this case, you're going to draw a line that best fits the majority of this data. It's not going to encompass every single thing. You're going to have outliers like this one and some of these. So you're going to put a line that is the best fit. A graph contains 5 major parts. The first, most importantly, is the title. The title depicts what the graph is about. By reading the title, the reader should get an idea about what the graph is all about. It should be a concise statement placed above the graph, such as the effect of whatever your IV is on the DV, the effect of your independent variable on the dependent variable. The independent variable is the variable that can be controlled by the experimenter. It usually includes time, dates, minutes, hours. It could be depth, such as feet or meters. It could be temperature, such as Celsius. This variable is placed on the x-axis or the horizontal axis. The IV is what I change. The dependent variable is the variable that is directly affected by the independent variable. It is the result of what happens because of the independent variable. This variable is placed on the y-axis or the vertical axis. The dV is how you measure this change. You will hear me say this many times throughout the year. IV is what I change, dV is how you measure the change. The scales for each variable. When you're constructing a graph, you need to know where to plot the points representing the data. In order to do this, we have to come up with a scale to include all those data points. This must also take up a conservative amount of space. It's not suggested to have a run on scale making the graph too hard to manage. The scale should always start with 0 and climb based on set intervals, such as multiples of 2 or 5 or 10 or even 100. The scale of numbers will be dictated by your data values. And then finally, you need a legend to your graph. It's a short descriptive narrative concerning the graph's data. It should be short and concise and placed under the graph. This would be useful if you have a multi-line graph explaining the differences in the two lines. When we're dealing with very large or very small numbers in science, we oftentimes need to use scientific notation. Sometimes when you put numbers into your calculator, whether it's in math or science, you may get a funny looking number on the calculator, not understanding what that is. Most generally, it's scientific notation. So just as we use metric prefixes, we can also use scientific notation to represent a very large or very small number. The important thing is that using scientific notation gets rid of a whole bunch of zeros for us. The values of a simple number, so something between 1 and 10, are multiplied by a power of 10. So our speed of light is 300 million meters per second. In scientific notation, we can get rid of all these extra zeros, and we can just write 3.0 times 10 to the 8th power meters per second. Scientific notation examples, 10 to the 3rd power would look like this, 1,000. 10 to the 2nd power would look like this, 100. 10 to the 1 power looks like this. It's just 10. Those little superscripts, those numbers like Superman flies in the air, a superscript is a number up above, and those tell us how many zeros we're trying to move the decimal place. 10 to the 0th power is just 1. That means that there are no zeros. When we get into the negative superscripts, like a -1, then we're going to start moving that decimal point and making our numbers less than 1. So 1/10, 1/100th, 1/1000th. When we use scientific notation, you're going to want to save this information right here in your notes, highlight it, circle it, star it, something to come back to it. When you multiply two values, you multiply them as normal, and then you add those powers of 10. For example, 5 times 10 to the 5th times 5 times 10 to the 5th. 5 times 5 equals 25. Then I'm going to add my times 10 to the whatever power. How do I come up with that whatever power? I go back and it says add the powers of 10. So that's that superscript number. So 5 plus 5 is 10. So it gives me 25 times 10 to the 10th. If we go ahead and put that into correct scientific notation, like we learn in class, you're always going to have that decimal behind the first real whole number. So 2.5 times what becomes 10 to the 11th, because I moved my decimal from here to there. So I moved it one more place. So that's going to give me another number for that superscript. When you divide two values, you divide as normal, and then you subtract the powers of 10. So it's just the opposite process. So 25 divided by 5 gives us 5. And then we're going to subtract 5 minus 3 gives us 2. So if we were to take this number out of scientific notation and put it into the whole number that it really is, we would move this decimal point that comes after the 5 1, 2 places. And this number right here would be 500. In your answer, if you have to move the decimal to the left, you add that many places to the power. If you have to move the decimal to the right because it's a negative, you subtract that many places from the power. We'll practice this quite a bit in class, so don't worry. A significant digit is important because you can only be as accurate as your least accurate measurement. This graphic shows the best representation: low accuracy and low precision. Low accuracy, but high precision means all of these shots are in a very tight grouping, so that gives me very precise measurement, but it's very far away from the center of that target. High accuracy, but low precision means I made quite a few of them right in the middle of the target, but low precision means they're not very close together. High accuracy and high precision means they're right on spot and they're very tightly grouped. Why do you have to work with significant digits? Because accuracy in measurements is important. You want to round as little as possible. Remember, when we round, 4 or below, leave it alone. 5 or above, give it a shove. The difference in calculators or periodic tables, all of those things will be eliminated when we use significant digits, and that means everyone will end up with the same answer. It can also depend on the instruments used. If you're using a metric millimeter ruler and your partner is using a tape measure that has the English units on it, you're going to have very different answers, even if you convert them over. So we want to make sure that we're all on the same page speaking, quote unquote, the same language. Significant figures show us how many figures are known for sure. All non-zero numbers are significant. Zeros within a number are always significant. So both the numbers 4,308 and the number 40.05 contain 4 significant figures. Zeros that do nothing but set the decimal point, they're not considered significant. So this number right here, 470,000, only has 2 significant figures. If we were to put a decimal point in there somewhere, then those numbers up to the decimal point would become significant. Again, we're going to practice this in class. Trailing zeros that aren't needed to hold that decimal place, they are significant. For example, 4.00 has 3 significant figures. Just because there's both zeros doesn't mean that that's not how accurate that measurement was. But leading zeros that come in the front, those are never significant. So you could have measured something 4.00 centimeters, It could have been that precise. Our significant figure examples, 1.638. In this example, we would have 4 significant figures. All 4 of these numbers would be significant. 1.6, you would have 2 significant figures. 0.0001, you would have 1 significant figure. The only thing that's important there is that 1. The number 500, you would have 1 significant figure. Remember, if there were a decimal point in there, that would change this number of significant figures. When using significant figures, your answer can only have as many significant figures as the smallest one in the problem. So this takes away the problem of asking the teacher, where do I need to round to? For this example, 54.2 centimeters squared times 22 centimeters. In this case, we have 3 significant figures here, but only 2 here. That means that your answer can only have 2 significant figures. It's only that precise. You can only be as precise as your least precise measurement. We don't just add a 0.00 on the end of it just to make it look like this one. This is the actual measurement we need to